In our human voice speech production system, lungs are the main source of the airflow that passes through the vocal tract, the oral cavity, then nasal cavity. Then based on the manner of articulation, place of articulation, we utter many different phonetic sounds. Now, in the synthesis, speech synthesis is the process of artificially generating the speech. Now, we are mostly aware of the text-to-speech synthesis processes. Now, in text-to-speech synthesis processes, we have the textual transcript, and we have a model that is trained for text, from textual transcript to the speech generation, audible speech generation. So, voice conversion is a specific type of speech synthesis process that comes under the paradigm of speech-to-speech synthesis. That means here the input is not a textual transcript, rather it is an audible speech, and the output also an audible speech. Now, how this voice conversion takes place? This is a schematic overview of voice conversion process. So here we have a source speaker and a target speaker. Now the source speaker can utter any speech in his or her language, and the target speaker can do the same thing. Now the basic objective is to extract the vocal texture of both source and target and superimpose the vocal texture of the target speaker over the content of the source speaker, such that it seems like that the target speaker is uttering what the source speaker has uttered. That is kind of deep fake speech generation. Now this voice conversion takes place in following a three-stage pipeline. The first is the speech feature analysis part, then comes this mapping, and then the reconstruction. So in the speech feature analysis part, we take the both source speaker and target speaker, we extract the features. We have different transformation techniques like mean substitution coefficient, MMCC or mean spectrogram. Then comes the mapping part, where we use statistical models or generative models like N and VAs and all. Then this model basically try to map the given speech feature of the source speaker to the target one. Now given this Y hat to this inverse, this reconstruction part, which is just the inverse of what the speech analysis part is. From the speech feature to audible speech generation. Now this three-stage pipeline takes place in two phases, that is training phase and the conversion phase. So in the training phase, we do the analysis part and the mapping part. Now once the model gets trained, in the conversion phase, we take any of the new sample from the source speaker speech, we do the speech feature extraction. Then because the model is already trained, given that speech feature, it can generate or synthesize a new converted speech feature, and then the reconstruction part does the from speech feature to audible speech generation.
Use the pointer, please use the pointer.
So actually it is not working.
The font is very small, so it's not easy to read.
Is it visible? So the voice conversion can be done in mainly two ways. One, using the statistical models and the deep learning based models. So initially people used to use a GMM, phonetic postogram, vector quantization. Nowadays people have shifted to deep learning degenerative models like GAN and VAs. Now these are the different types of voice conversions, like parallel, non-parallel, monolingual, crosslingual, intragender, intergender. Then another type of mapping is like one-to-one, many-to-many. Then there is also emotional voice conversion, disordered speech to normal voice conversion, then also singing voice conversion. So in parallel voice conversion, we have the parallel content of both source and target. It may not be time aligned, then you can use DTW. So in case of non-parallel VC, it may be same linguistic identity or not, but the thing is like the contents are not parallel. Now, voice conversion challenge 2016, they first proposed that data set for parallel speech content, and in DCC 2018 it is the non-parallel speech content in unilingual, that is only in one English accent, US English accent. Then comes the monolingual and crosslingual. So in monolingual, the both source speaker and target speaker belong to the same linguistic group, and for crosslingual it is different. Now crosslingual is nowadays widely being used for in the field of low resource languages, because in low resource languages we do not have very much speech sample recorded in specific speech content of that low resource language. So people are using in the source speaker for a specific linguistic activity. They are recording the speech samples, and the target speaker, you can use any target speaker recorded in any language. Then superimposing over the vocal text or over the content, they can use augmented data. So this is how the this cross-lingual nowadays is being used for this low resource languages. So BCC 2020 is one of the data sets, like it has been recorded in English, Finnish, German and Mandarin. Then comes the intragender and intergender. So in intergender, both the identity is same, whereas it is a intergender, it is a cross identity. And another type of voice conversion is nowadays it's also been widely used in many to many BC, where the mapping goes from the multiple source speaker and multiple target speaker. So for one source speaker, we have to train for all the target speaker. The similar way, like one-to-one, once the model gets trained, then given the speech feature of any source speaker, we also have to give the identity of the target speaker that we want in the conversion phase. I mean, the target speaker that we want to generate. Now, TFP belongs to that, CP belongs to the identity of the target speaker that get converted at TFP, and then after that you can reconstruct, the F inverse can reconstruct from the speech feature to the audible speech. Then another is emotional voice conversion. So emotional voice conversion, there, I mean, till now the dataset exists, ESD dataset just recently in 2022 it has been published. So it has the parallel speech content, the speaker identity remains same, but in different emotions it has been recorded. So the objective is given, once the model gets trained for different emotions, given a new emotion, what will be the, I mean, the target emotion you want. So that is how the emotional voice conversion takes place. And another one is like dysarthric to normal voice conversion, when speech disordered speech to normal voice conversion, where the formants are not well formed. That means if the speech uttered by the disordered speaker is not very well understood. So in that case, the models are trained with parallel speech content of both the dysarthric speech or some other speech disorder patient and the normal speech. So once the model gets trained, in the conversion phase, they are given a new speech content that can approximate the exact formats such that we can understand what the speaker was trying to say. There is another type of voice conversion, the singing voice conversion. So here we have the vocal of different singer from source and target, and we do the same thing, but in the till now the dataset that is available, that is singing voice conversion 2023, here only the vocal part is present, not the musical content, composition. Only the vocal part is there that we can use for voice conversion. Now these are the objective evaluation metrics that is widely used. MCD, MSD, FGO, RMSE, there are other objective evaluation metrics that are also there, and subjective MOS and APX. Now there are some certain things that I like to discuss with everyone there. The lower MCD score tells us that the feature similarity is very, it is very highly similar. Whereas the MOS also tells us, high MOS tells us that how, in terms of the subjective evaluation, the subject, how they evaluate and whether the similarity is high or not. Now the correlation, we try to evaluate establish the correlation between this subjective and objective. Then most of the cases we have found that there is a positive correlation among the objective evaluation matrices. But some of the time when the linguistic identity got changed, for example cross-lingual or intergender, cross-gender voice conversion, then it is not like you can generalize the relationship. Sometimes it also get differ. Then there is a generative adversarial network and generative adversarial network based voice conversion. So we know that in a generative adversarial network we have a generator and discriminator. So the basic objective of the generator is to given two distribution, source distribution and target distribution. The generator try to map the source distribution to target distribution, and you have the discriminator which is trained with the original target data, and it tried to, every time it tried to classify whether the generated, that y hat, here it is the generated one, whether y hat belongs to the real class or fake class. Now this is the objective function which the generator, the discriminator wants to maximize, and the generator want to minimize. So it's also called a min-max game or zero-sum game. So at a certain point of time, when the Nash equilibrium state is obtained, at that moment of a discriminator is unable to classify whether the generated sample belongs to real or fake class. So it gives directly the probability of 0.5, that is equal probability of belongingness of real class and fake class. At that point of time, we say that we have obtained the target distribution. The same thing we have, nowadays people are using for voice conversion. So here we have the generator that maps the source speech feature to the target speech features. Now there exists a discriminator. Every time it try to classify whether the y hat belongs to real or fake or not. So once we obtain the Nash equilibrium state, then the y hat becomes very similar to y, and then we can feed it the vocoder that for the reconstruction of the audible speech in target speaker voice. So these are the few baseline models. So these are CycleGAN VC. So it is based on the CycleGAN framework that we initially used for style transfer in image to image synthesis. Then these are the other variants of CycleGAN, and the most recent one is the Mark CycleGAN VC. And this StarGAN is for many to many voice conversion, and its current variation is StarGAN VC2. Now this is the CycleGAN VC framework that is being used for the style transfer in image to image synthesis. Now here you can see that we have zebra in the source domain and we have the horse in the target domain. Now the objective is to superimpose the distribution of this horse over the zebra and vice versa. It is a forward mapping and reverse mapping you can see here. Now at the same time you have to keep track whether any distortion has happened to the shape of the source. That means we want to, at the same time we want to preserve the content. Only we want to transfer the style of the target over the source. So that is how you can see that GA to B is mapping the source from source to A to B, and once we obtain the B, then the discriminator is trying to classify whether the B belongs to the real class or not. After that, GB to A again try to reconstruct the B domain to A domain, and he try to using L1 loss, which is also called as cycle consistency loss, try to map with try to understand whether the content information has been distorted or not. Now the same thing has been used, the same concept in CycleGAN VC. This is the CycleGAN and this is the CycleGAN voice conversion. The same thing has been used, that whether the content information we can preserve it, because we do not want the source information, the content information, linguistic information to get distorted. We just want the target, local style of the target to get superimposed over the content of the source figure. Now this is the working mechanism of CycleGAN VC. So initially it has been trained for use world vocoder. So it is a statistical vocoder. So initially the speech features are being extracted. The mapping for MCC is only done using the CycleGAN. Others are not using. For other map like F0 and aperiodicity, they are not. They are statistically they has been mapped. Only for the MCC, the middle statistical coefficient, this GAN model is CycleGAN model is being used. So once the mapping is done, then the world vocoder is again reconstructed to the converted speech to target speaker vocal texture. So this is the Mark CycleGAN, the latest variants of CycleGAN VC. So it is based on the concept of filling the frame. So what is the fill in the frame? So say for example, in terms of computer vision, if you understand that we have given an input of a sketch of some person, and I want that the strokes of the Van Gogh painting get superimposed over the sketch. So for that purpose, the filling the frame concept are being used. That means the filling this sketch part, which is where there is no pixel distribution is there, with some target distribution. So here a mask is being concatenated with the input. Now the objective of the generator is to fill that this blank parts with some target format distribution. Now again, such that the linguistic information do not get distorted, again G Y to X try to reconstruct to the X domain, and using the cycle consistency loss, it also always try to map whether the distortion has been happened or not. So based on this concept of max cycle again BC, so we try to do some modification to it. So our main objective was like the whole voice conversion process takes place first mapping, then generation, then evaluation. So once we have the audio sample generated, then we evaluate using different evaluation matrices that I have already mentioned. Now we tried that whether we can use that evaluation matrix, the feature specific evaluation matrix in the training only. With the, already the cross entropy loss is there or N2 loss is there. So additionally, whether we can use the evaluation matrix as a loss function to the for training. So based on that, there is a specific metric, the fetched insertion distance. So it is used in the field of computer vision. So when you can see in the leftmost image is the original image and the right images are the generated one. So FID matrix helps us to understand whether any distortion has happened or not. So this is the in a univariate normal distribution. This is how we can find, calculate the distance, Frechet distribution to distribution x and y, and this is for the multivariate distribution. This is the formula for FID. Now using the FID, people try to evaluate whether their generated samples are very similar to the original one or not. The same metric we try to use in Mark cycle again model, that whether so whether the generated samples that you are obtaining, whether we can do the same using the same metric, we can find whether we have obtained the similarity or not by tracing this similarity during a training time, whether we have obtained the best male spectrogram in target speaker voice or not. So for that purpose, we have used two discriminators. The first one is the inception model, V3 model. So we are using the feature embeddings. The generated male spectrogram we are taking as an input, and then we are getting the feature embeddings. So you can see that the FID, we are the first one is the IY. The Y is basically the original one, and the Y head is the feature embedding of the generated one. So we compared using the FID metric and then other discriminator that we have. So it is a normal patch again. So here we have used the sigmoid, like if DY and the feature embedding of original and the target one is very similar, then the sigmoid will be tends to 0.5, and if it is not similar, then it will be very high. So minimizing that, we can find that whether the generated male spectrogram and the target one is similar or not. So this is the building block of the generator. Then we used another normalization technique. So we are mostly well familiar with this batch normalization, instant normalization, group and layer normalization. Now position normalization is a kind of is a different variant of normalization technique where the normalization takes place pixel wise throughout the channel. And region normalization is another type of normalization techniques where people use it for image this inpainting task. Where there is a masked part, where is an unmasked part. So the normalization takes place separately for the masked part and the unmasked part. So what we did is we combine these two. That is because in our image also we have usually used the masked of the male spectrogram. So we have separately used the this normalization for masked part and unmasked part, and use the position normalization, that is a pixel wise normalization throughout the channel. And then we have used this variant of gated linear image, that is Gaussian error gated linear GEGLU. So what is that? In language models, so in gated convolution neural network, so when you have the textual transcript, we obtain the feature embeddings. Then we apply two convolutions. So you can see the E is the feature the embeddings, and EW plus B. So at the first convolution, then E into V plus C, this is the second convolution. Now that is multiplied with the sigmoid operation. So sigmoid operation help us, if it is tends to 1, that means that information, it has a high information, and if the sum of the information tends to 0, in the vector, then it implies that there is not significant information present. Now the same thing has been used in the computer classification tasks using MNIST dataset. So GEGLU is a variant of this GLU. So you can see that it has obtained the faster convergence in very small, less number of epochs. The loss is very less and the accuracy is also very high. So we try to incorporate the GGLU to our model. And this is the relativistic. So this part is the relativistic discriminator that I have already mentioned here, and this is the FID part using insertion V3. So these are the dataset we have used. This is 2018 and CMOIT dataset, and we have used this. These are the speaker identities that we have used. We have used 81 samples for training and 35 for testing or for conversion part. And we have also tried to evaluate the robustness of our model for equal dataset, the Dizerthi dataset. So these are training details. So these are the objective evaluation metrics. So you can see that the MCD and MSD and F0 so for our model, the FID RPR, mostly we have obtained the very less. As compared to Marxalian, our score is very less. That implies that our generated samples are more similar to that of the target one. Then we have also done the ablation study. So in order to find the impact of each of the contributions we have made to the model. So which impacts more to the model, contributing more to the model. So this is how we have done the ablation study. So and this is the mean opinion score, and here you can see the spectrogram and visual representation of the mail spectrogram. So this is the Dizerthi speech, and this is the normal speech for this parallel speech content. So what we did is we tried, we used the model, the FID RPR gun, and we tried to evaluate whether we can superimpose the vocal texture of the Dizerthi speaker over the normal speaker, that is to get the content, such that we can generate augmented data in target speaker, that is Dizerthi speaker's voice. So this is the Marxalian VC and the FID RPR VC that it can be very well, you can see that in the second region, so the formats are very not well formed using Marxalian VC, whether in case of our FID RPR VC, the formats are much well formed. The pattern can be, the format pattern, the first few format pattern can be well, you can visualize. And this is the conclusion, like what are the models we have, dataset we have used, and our feature scope is like you can use it for the multilingual voice control. So this is for unilingual, for the US accent, English US accent we have used. So this can be also experiment for the multilingual setting. And these are some other publications from our recent publication from our NIT-Durgapur VC lab. So we have also done for many-to-many voice conversion as well, and one-to-one voice conversion, and one similar kind of work we have done where that would accept in iCares, where we have used the MSD metric for training, like instead of FID. Thank you.